Ever wonder how AI can learn from complex webs of connections, like social media, molecules, or even the internet? Today, we're diving into a breakthrough technique called LaplaceGNN, which uses advanced math to teach machines to see graphs in a smarter way. Let's break it down. Graphs are everywhere, friends on social media, neurons in your brain, or websites linked together. But how do we teach AI to learn from these? Traditional methods often rely on negative samples, like telling the AI, "This isn't a friend," which is computationally heavy. LaplaceGNN flips the script. Instead of hand-picking examples, it uses spectral properties, the math behind a graph structure, to create its own learning opportunities. Here's the trick. It starts by identifying key nodes using centrality measures. Think of these as the stars of the graph, like popular people in a social network or critical hubs in a transportation system. By focusing on these nodes, LaplaceGNN generates augmented views of the graph, tweaking connections in a way that challenges the AI to spot what stays the same despite changes. But how does it do this? The magic happens in two steps. First, it uses Laplacian optimization, a method that adjusts the graph's mathematical fingerprint to create two contrasting views, one where the structure is maximized, emphasizing changes, and another where it's minimized, keeping things stable. This ensures the AI learns robust features without getting confused by random noise. Then comes the adversarial bootstrapping part. Imagine a teacher-student setup. The teacher network creates tricky perturbations, like adding or removing edges, to test the student network. Instead of relying on negative samples, the student learns by matching the teacher's responses. This not only speeds things up, but also makes the model more resistant to malicious attacks, like someone trying to mess with the graph structure. The result? A system that scales efficiently, handles complex graphs, and generalizes better to new tasks. Whether it's recommending products, analyzing scientific data, or securing networks, LaplaceGNN shows how math can turn chaos into clarity. But how do we know these innovations are trustworthy? Let's talk about the science of scientific rigor, the guidelines that ensure research is transparent, reproducible, and ethical. First up, reproducibility. Imagine a paper claiming a groundbreaking discovery, but no one can check the work. These guidelines say, no, papers can't just be rejected for missing code, unless the code is central to the discovery. If you publish a new AI model, you must provide the exact commands, data, and environment needed to recreate the results. Think of it like a recipe. Without the right ingredients and steps, no one can bake the same cake. Now let's talk experimental details. A good paper doesn't just say, we trained a model and it worked. It tells you how, like the exact datasets used, the hyperparameters, those are the settings for your model, like learning rates, and even the optimizer type. The paper we're looking at here. It's thorough. It lists everything from data splits, how the data was divided for training versus testing, to the specific neural network architectures used. And if some experiments can't be fully replicated, they're upfront about it. But wait, how do we know the results are reliable? That's where statistical significance comes in. The paper here reports mean and standard deviation across 10 random trials. Why? Because science isn't about one lucky experiment, it's about consistency. Standard deviation shows how much results vary, helping us spot if the findings are just flukes. They even mention the sigma levels, which tell us how confident we can be in the data. Think of it like a weather forecast. If the error bars are tiny, you can trust the prediction more. What about the computing power needed? Some experiments require supercomputers or GPUs. The paper here tells us they used a 24 GB RTX 4090 GPU, and even notes when models ran out of memory. But here's a gap. They didn't mention how long each experiment took. Still, transparency is key. Without it, others can't replicate the work efficiently. Now let's shift to ethics. The paper claims to follow NUR-IP's code of ethics, which covers things like fairness, privacy, and avoiding harm. Since they used public datasets and no sensitive data, they're in the clear. But here's a reminder. Even if a study seems safe, researchers must always ask, could this be misused? For example, if their model could be exploited for biased decision-making, that's a red flag. So here's a secret ingredient in the science world that's way more than just lab coats and equations: anonymity. Imagine submitting a paper to a big conference like NUR-IP's, but your name, university, or even your lab's logo has to disappear. Why? Because science needs to be fair. Think of it like a talent show where judges can't see the contestants' faces. No bias, just raw talent. Reviewers need to judge work based on its merit, not who wrote it. It's the ultimate test of whether an idea stands on its own. But here's the twist. Language models like GPT are now part of the game. Conferences are asking a critical question. Is this AI a co-author or just a spell checker? If a paper uses LLMs to generate core ideas, analyze data, or shape the research direction, authors have to explain exactly how. But if the AI is just helping with grammar, formatting, or polishing prose, no big deal, no disclosure needed. It's all about whether the AI is driving the science or just cleaning up the mess. In this case, the answer was nah, meaning the research didn't rely on LLMs for its big ideas. Why does this matter? These rules are the invisible scaffolding of science. They keep reviews honest, prevent shortcuts, and make sure we're clear about how tools like AI are used. Whether you're a student, a researcher, or just someone who loves how science works, these details are part of the backbone that lets breakthroughs happen. Thanks for sticking with me. If you want to dive deeper into how AI shapes research or why anonymity matters, check the links below. And if you enjoyed this, hit that subscribe button, because the next video is all about how AI is rewriting the rules of discovery. See you there.